Good afternoon. Sorry to make you wait. I was changing my setup at home. I hope you can hear me. Let me know if anything is noisy or delayed. Give me some feedback on what you are experiencing. What I'm going to do today is, well, I didn't hear from anybody about the mock exam, so I'm going to assume you have no questions about the mock exam unless you post them here. I'm going to solve this problem that I left for you yesterday. There's 2 exercises in one. And then I just posted 2 more. I said I would post them last night, but again, I didn't do it. I just posted them now, so we'll go through them. And then there are some remaining questions that someone sent me that I'll look at. And then anything else you want regarding the mock. So I'm doing these extra problems, but really the mock exam is the format for the problems that you should be rehearsing, okay? So make sure that's your priority, is the mock exam. Now tomorrow's the exam, so you have tonight and tomorrow. Let me know if you're stuck anywhere, you don't know how I derived an answer. Just let me know, but I haven't heard from anyone, so I don't know if that's because you didn't complete the mock exam yet or because you don't have any problems. But please let me know once you do complete it if you do have questions. So tomorrow I'll meet you again at 5, and then you'll start the exam at 6. There will be no more makeup quizzes. We did lots of opportunities. I need to post all your grades for those, I know. Again, I apologize. It's unbelievable the amount of work I've had to do, and this week I was really burnt out as a result. So I'm looking forward to tomorrow, the final exam. I need to post it still. So as I said, I'm going to post the multiple choice in Moodle, and so you can solve the multiple choice section, and then for the short answer, you can call it long answer section, you can solve them and send me the answers by email. All right, and I'm going to ask you to put a subject title on it too, so I can keep my emails organized. All right, so let's see how you did with this problem. Coke and Pepsi. Coke and Pepsi are the 2 most popular colas on the market. Do consumers prefer either one of the 2 brands of cola over the other? We conduct a match pairs experiment as follows. 20 volunteer participants in blind taste tests. Each volunteer tastes both. So remember, the match pairs is that the subject gets both treatments, okay? And scores the taste of each. Okay, wait. Each volunteer tastes both Coke and Pepsi in a random order and scores the taste of each cola on a scale of 0 to 100. Some information that may be helpful is shown in the table below. All right, remember, this is match pairs. When it's match pairs, you ignore this information and you just use the differenced information, all right? So don't get confused. 80% of students by the end forget this and they start using these numbers and getting very baffled. So as long as it says match pairs, or I give you sets of data, like I pretty much tell you, this is given to you. If I give you 2 sets of data and they're related or dependent, you can subtract them from each other and collapse them into one set and calculate mean and standard deviations. All right, so otherwise you won't be able, with this information, to compute a standard deviation for both, the difference of both. All right, so which of the following statements is true? The scores for, okay, so we're going to go through each one. Actually, why don't you guys tell me which answer you chose? Let me know which answer you chose. Nobody? Nobody tried it? Yeah, I kind of gave it away in my description. No comment? All right, so let's go through each one, and then you can, when you feel confident, you can tell me how you feel. Oh, one sec. Okay, no comments. Okay, so the scores for Coke and Pepsi for each individual are independent. That is not what we want. That is not true. In fact, the scores are dependent, right? Because it's the same person. So dependent is correct. In order to conduct the matched pairs t-test, we must assume that scores for Coke and scores for Pepsi both follow the normal distribution. For the matched pairs t-test, that is not necessary. Remember, these are the same results from because we had how many in our sample? Going back up. 20 volunteers, okay. So this is not required for the matched pairs t-test. And I'll go back, I'll show you in the notes where I have that, but that's not true either. In order to conduct the matched pairs t-test, we must assume the differences in scores follow a normal distribution. All right, so the fact is that we are going to be testing the differences, right? It's the differences that we're interested in. And the differences, let me show you now. Let me show you where that is in the notes. So this is the theory about t-distribution. I hope that you were reading through the notes. The t-distribution, I have a discussion here with sigma unknown. Okay. So when you use a t-distribution, I have in a box here. So when you use S in place of sigma, it means that the standardized evidence, right, the standardized mean is going to be t-distributed with the degrees of freedom n minus 1. You can use S, and we have to make this, okay, it's not exactly clear, is it? Okay, so the t-distribution arises provided that either the underlying population is normally distributed or close to normal. So that's why I wrote this. Okay, so this corresponds to this statement. Or that you have a large sample, you have a large sample size, or larger than 30, if the distribution is skewed, and if it's symmetric, you can use this result as long as you're told it's symmetric if the sample size is between 15 and 30. If it's smaller than that, you can't do it. So these are the conditions. Now you're just going to have to know where to go if I ask you any questions about the assumptions, but essentially there are assumptions underlying this, that x, the variable that you're going to test, is normally distributed, or if it's not, that the sample size is large enough, or if it's not large enough, that it's symmetric at least. Okay, so get your head around those assumptions. So in fact, it's not the actual value. So this is just for the variable analyzed. So the variable analyzed is the difference variable, not the not the two separate ones that are dependent. It's the difference data. So that's why that statement is being made. All right, so that was page, oh actually, should I tell you what page that was? It's not going to show me now. That was when you start the T stuff, that's over towards the bottom, and that's page, sorry, here. So that is page 36, okay? This is page 36. Of the inference notes, that you'll see that. So let's go back to where we were. Okay, here we were. So that means that, so reading it again, in order to conduct the match pairs t-test, we must assume that differences in scores follow a normal distribution. So there's no information, there's no way of knowing that, but we'll have to make that assumption to actually do this. Okay, so normal means that, you know, we know the shape of a normal, but it basically means that most of the values are going to be centered around a certain value, and then they're going to be spread out evenly on both sides, you know, higher and lower than that value, and then much higher and much lower than that value. It's a regular type of distribution, so we're saying that the differences will be sort of regular in that way. All right, so then that leaves us 2 and 4, so the answer is E. All right, so that was a little bit challenging because you had to go into the notes and you might not have known where that was, but there you go. All right, so next, what are the hypotheses for the appropriate test of significance? So what do we want to test again? We want to see, let me read this again. Do consumers prefer either one of the two brands of cola over the other? So we want to see if one scores higher than the other. So what we'd expect to see in that case is, you know, okay, so let's say the opposite. The opposite of that is that they're the same. If they're the same, then the difference number should be 0. If it's not the same and one is higher than the other, so depending how we subtract, if Coke is better than Pepsi, we expect this to be a positive number. If Pepsi is better than Coke, we expect this to be a negative number. So what we're going to be testing, so let's look at the options, all right? So let's do this by process of elimination. Process of elimination means that, remembering that I taught you all hypotheses are going, for means, are going to look like that. Right? So that means B is out. B is out. And D is out. Right? Okay, so then the number that we're going to put here is 0. That there's no difference. And that's the status quo, that there's no difference, right? And we're looking for some difference. So they're not the same. That's how we do that. So that would be option E. How is that? So that's option E. Is that okay with everybody? So I get E. Any debate? Okay, next one. Assuming the appropriate assumptions are satisfied, what is the value of the test statistic for the appropriate test significance? So for this, assuming the appropriate assumptions are satisfied, what is the value of the test statistic for the appropriate test of significance? The test that we're going to conduct for matched pairs is a t-test, and we do a t-test of the difference data. We conduct a t-test, we standardize our evidence of the sample mean of differences, and we test if it's different from 0. So we just need to calculate the test statistic. It's just one of the 5 steps. So so the test statistic is the mean. Sorry, not that. We're going to use the mean, the sample mean, right? The test statistic is the sample mean minus the hypothesized mean test over root n. The hypothesized mean is 0. The S we got from the sample, and X bar we got from the sample. So the data that we got was all about the sample. That's why we have to use this formula. So putting all the values in there, I'll do it up here with the numbers. So it's going to be, again, the t-stat, this is my statistic, this is what's calculated from the sample, is -5 minus 0, the hypothesized mean, divided by S, divided by square root of n, and n was 20. So that's it. That's all we plug in. It's negative. I'm just checking. I get negative 1.72. That's my answer. D. If you can see that. Okay, so the answer is D. So did I do that right? 5 negative divided by S and multiply by 20 square root. And I don't have to do anything else. Just checking something. Okay. Okay, what I want to do now so what I want to do next is go to the problems, the new problems. Some problems I just posted, which you probably, you haven't even seen. So let's see if I can post those. So I said I would backtrack a bit. Very good, Antonio, I'm glad. Glad you got the answer. Okay, I'm just loading. That's not what I wanted. Okay, let me do this again. I'm going to, let's just go to these ones and then I'll figure out what I did wrong there. Okay, so these were sent, these I guess are problems from the homework or review. Okay, this looks like a homework problem. So these were sent by a student. It is desired to estimate the mean dining room and bar tab for parties of 4 which dine at a particular restaurant. The resulting confidence interval should have a width of $10 and a confidence coefficient of 95%. A reasonable value for sigma is $25. The required sample size is, so for this, you're given sigma, right? So going to the formula sheet, you're going to use the formula for means. So that's going to be for inference on the mean, sigma known. So you're going to use the formulas in row number 5. So in row number 5, you're going to apply the zoom formula. So that is that n is equal, let me use it blue, n is equal to z sigma over m squared. The only thing that's catchy here, you want the critical value for z, right? The only tricky thing is to realize the width, remembering width is the whole interval. The whole interval is 2 margins, so 2m. So if the width is 10, then the margin is 5. That's the only real tricky part. Well, not tricky, but that's the only interpretation that's challenging. So then you put all these numbers into here. You put all these numbers into here and you find n. Don't forget to square. And so you can let me know if I got the wrong answer, but I'll plug it all in. For 95%, Z star is 1.96. So you multiply 1.96 times 5 divided by, no, I did that wrong. 1.96 times 25 divided by 5 equals squared. It's 9604. So the best answer, remember we have to round all the way up to the next person. The best answer is 97. So it should be C. Okay, here's another problem. In some mining operations, a byproduct of the processing, let me just double check what happened to a file. Hold on. You guys can try that, read that problem. Okay. So in some mining operations, a byproduct of the processing is mildly radioactive. Of prime concern is the possibility that release of these byproducts into the environment may contaminate the fresh water supply. There are strict regulations for the maximum allowable radioactivity in supplies of water. In order for the water to be safe, the population mean radioactivity level must be less than 5 picocuries per liter. A random sample of 25 specimens of water from a city's water supply gave a mean of 4.61 and a standard deviation. Again, reading these problems, you have to differentiate between the sample and the population information. Here, all you have is the sample result. 25 is N, the mean X bar is 4.61, and S is 0.87. There's no information here on sigma, right? So the test, what we're testing you here is that you can state the hypothesis and if you know the right test. So we wish to see if the data provides sufficient evidence to declare that the water is safe. So there's strict regulations. So the radioactivity level must be less than 5. Right. Well, remembering we have to make a statement with an equal sign here, and if that's not true, then the next thing has to be true. The alternative has to be true, right? So what number is going to go there? It's going to be 5. That's the number they gave you. And now, what's the sign? So the assumption is going to be so no problems, no issues, status quo, that it's that it's safe. We'll state the status quo as though it's safe. So then this should be less than, right? For it to be safe. It should be equal and less than. So the opposite is that it's unsafe. To be unsafe, then it should be greater here. Remembering that we don't write the sample mean here or here. I'm going to test that it's greater. That would be that it's unsafe. Because we operate that with the regulation that it's safe. And so the answer should be D. If there's any problems with that, let me know. I'm not sure where these problems were taken from. It looks like they were from the review exercises. Okay. So what are, respectively, the distribution of the appropriate test statistic and its value? In this case, it's the t-stat, right? We already discussed that because we don't have any other information. We're going to calculate a t-stat. And the t-stat is going to be the evidence minus the hypothesized value divided by the standard error, which is S over root of n. So putting all that together, x bar is 4.61. So 4.61 is smaller. It looks like it's smaller than 5, so it's probably going to be okay, right? Minus the hypothesized value, and then divided by S, which is 0.87. Oh, geez. Sorry, it's so messy. Divided by square root of n, which was, what was the samples? Sample size. $25. I always have to check because I always remember the earlier problem. So 25 square root. So this is a 7. My goodness. Okay, so then putting that together, sorry for the mess, write it out yourself. So that's 4.61 minus 5 divided by 0.87 times. So I get negative 2.24. I get this one. And with 24 degrees of freedom. Okay, any questions about that? Hi, Carolina. That's what I get. I think there's one more problem. I think it was Carolina who sent it. And then I'm gonna just do these ones. Okay, so these are the additional questions I added. Oh, no, they didn't show up. Wow. That's not what I want. I need to clean this up. I'm not finding. Pretty sure. pretty sure that was it. Oh, we just, sorry, was the video getting distorted? I got some complaint from YouTube just now. Jan, it's not Z because there's no sigma in the problem. There were no... It's not showing my most recent post. Oh, I'll just get them from here. So what I posted a student driving to the university. Sorry. Okay. All right. Okay, so this is at the end. Okay, this is it. So why don't you try this one? I'll give you 5 minutes to set that up. So this problem is in the homework exercises I just posted today. So let me give you 5 minutes for that, and I'll check back with you. Okay, so I've just showed you that you need to build a matrix, okay? This is the matrix. Oh, you can't see my yellow. So this one says yellow. I'll highlight my yellow. So those are all the possible outcomes. There's 9, and I've listed them here. Okay, so you just imagine all possible pairs. Now for the next question, the next part is, what is the probability that both sets of lights are the same color when the student arrives at the respective intersections? So what's the probability that it's the same color? So out of all the possible outcomes, the same color happens here, here. So let's say it like this. It happens here, G and G, or Y and Y, or R and R. So by or, you know all I have to do is sum those probabilities. So what you're doing is you're calculating the probability of G and G, or YY, or R and R. So each of those, because one light is independent of the other, we're going to assume that, or we can't do this. So we'll assume one light is independent of the other. So I'm just going to multiply these probabilities for each one and then sum the pairs. So that's how you get that result. Does anyone have an answer for me? So the chance that the first one is green if you look up at the problem is 50% of the time. And the chance that the second one is green is 60%. Right? And then you're going to add that to, the first one is yellow, which is 10%. Multiplied to the second one is yellow, 10%. And then the last is that both the first and the second are red. So it's 40 times 30. Okay, so that's that, and when you put it all together, you should get 43%. So that's pretty good. 43% chance of them being the same color. Red and red would really suck, but anyway, there you go. Then the next question is, what is the probability that the first light is green or the second light is red? So which alternative is that? So you do the same sort of thing. Okay, so this is just probabilities. This is just probabilities. The first light is green, or the second light is red. Second light is red. So what you're doing with or is the first light being green is this entire row, and the second light being red would be this entire row. So it's any of these and these. Okay, so you identify them in the set and you add their probabilities together. That's not hard. I'm not going to do it. That's quite elementary. I'll just tell you the answer. The answer, you can double check, verify that. The answer should be 65%. So this one was 43%. And this one was 65%. And for the last one, the probability distribution, looking at all the possible outcomes, let X be the number, so we're going to reorder the outcomes. Let X be the number of red lights encountered by the student on her way to university. So either she could get, the possible outcomes are let me do that again. Ooh. So the possible outcomes for X are no, 1, or 2, right? So what's the probability of no red lights? What's the probability of 1 red light, and what's the probability of 2 red lights? So you have to go through your table and sum those probabilities together. And the answer should be 0.42, 0.46, and 0.12. All right, so that's just using independence. Oh my goodness, so sensitive. That's using the property of independence and the rules of probabilities. So just try those, see if you get the right answer. Let me know if you have any questions. If you can't get it, don't spend too much time on it, but you should be able to get those answers. The other question I posted was about computing a proportion, making a confidence interval, and conducting a hypothesis test. Do we have time for it? You guys can stick around or you can go. I'll solve this one as well. Okay, so that was that one. This is the other question I posted. So Canadians do not seem to like Donald Trump. We'd like to estimate the true proportion of Canadians who support Donald Trump. In a random sample of 400 Canadians, 80 of them say they support the American president. So 80 out of 400 is how much? It's 20%. So the sample result is the sample proportion x over n, which is 80 out of 400, or 20. So there's three things we're going to do. We're going to calculate a 90% confidence interval for the true proportion of Canadians who support Donald Trump. You're going to use the formulas in row number 4 for proportion and calculate you're going to calculate p hat plus or minus Z star times the standard error, which is p hat 1 minus p hat over n all square root. So when you put all that together, you should get a very small interval, 0.1671, and with upper limit 0.2329. Very small. That support Donald Trump. That's with using the p hat that you computed here, the 20%, and the z star for a 90% confidence interval. Is 1.645. I believe. That's what we used from the T table, we got that, right? Okay, second part. Conduct a hypothesis test at the 10% level of significance to determine whether there's evidence that the true proportion of Canadians who support Trump is less than 25%. Well, now, setting this up, we need to set up the hypothesis. This time, right, we're going to use P. The parameter of interest is the true proportion, not the mean. So don't forget how to do these kinds of problems. And this is still an equal sign, and whatever number I put here, I put below. The question is about whether it's 25% or not. So 25% goes here, and it also goes here, and then I want to test that there's evidence that less than 25% support. So where the null hypothesis is 25 or greater, that's what that implies. I'm going to test it against 25%. Even though it's 25 or greater, I just write it this way. Oops, I don't put the greater in, okay? I always put an equal sign. It's pretty much implied by the alternative. Remember, these are the P naughts here, the hypothesized P, hypothesized true proportion. So then from there, we take the next step would be assume that the null is true, and with that we know that the proportion, the estimate for the proportion p hat is approximately normally distributed, and so we use that to standardize our evidence and test how far away or how different it is from the true, the hypothesized true proportion. So the value we got was 20%, and it's already small, right? So it's the p hat was 20%. So it is pretty small, but the question becomes, small enough? Is it far enough away for us to say it's very strange enough to suggest that less than 25% of Canadians support him? Well, the whole confidence interval was below 25% anyway. So it's probably true. So let's just check. Let's check with calculating. Now we're going to calculate a z-stat. Right? So don't get confused when you're going between t and z. Make sure you write it down. The z-stat is the p hat minus the hypothesized p divided by the standard error, which is p hat 1 minus p hat over n square root. So we do this because we don't know p in advance. We're just estimating. We're using our best estimate of it and assuming it's exactly true. Oh, actually, sorry, I need to correct myself on this because it's not p hat, it's p0 that I put here, right? The hypothesized one. Usually I put the step in, the assumed step, so I don't miss that, right? Because the standard error, because of the assumption, I assume this is the mean, and then this is the standard error. So putting all this together, this is equal to 20, minus 25 divided by 25, 75, and 400 square root. So make sure you punch that all in properly. And you should get negative 2.31. This is a left-sided test, so we draw the the z distribution, put it there to remember which table I'm looking at, and I plot negative 2.31 on the left according to the alternative hypothesis. I want to check what's the chance of being out there. What's the chance of being as far or further than negative 2.31 standard deviations? So when I look that number up, I get 0.0104. It's very small. Where I've been given alpha equals 10%. So that is smaller than 10%. So we do have evidence to reject the null in favor of the alternative. And the conclusion, to state the conclusion, so I'll write that out as I usually do. So p-value less than or equal to alpha means reject, so we have a significant result. In our case, our p-value that we computed was 0.0104. That is smaller than 10%, because that's what we were given. We're told to set it. It's strange if it's smaller than a 10% chance, yet we observed that, that number of people, that number of people actually supported him. And so this is true, so then we reject the null hypothesis and say, no, there's actually evidence to suggest that the alternative holds. So the way you would say this would be, a full statement would be, if the true proportion so this is not the concluding statement. This is a statement of what the p-value means, okay? That's what they asked for. So if the true proportion of Canadians who support Trump was 25%. The probability of observing a sample proportion at least as low as 0.2, or I'll say 20%, would be one, or I'll say 0.0104. Okay, so that is that. That's how you interpret the p-value. It's the probability of seeing a result as extreme or more extreme, assuming the null hypothesis is true. So that's a statement of the p-value. So those are the kind of exercises that I can give you for these last two, are the kinds I would give you on the long answer section. Okay, so if you have any questions about the mock, just work on the mock tonight. If you haven't already, if you have worked on the mock, then there's lots of exercises to try. And I wish you good luck. See you tomorrow. Keep in touch. Bye.